Hi everyone, I hope my screen is visible to you and I'm audible. Today's class is going to be about oral radiology. So we will be discussing about the basic principles, about the equipment and everything, and also about the interpretation. So I'll be taking it in two portions. Okay. Before starting with oral radiology, everybody should be familiar with this person who introduced oral radiology. He is the man who made invisible become visible. Okay. He is the W.C. Roentgen who invented the X-ray. Okay. So when it comes to, sorry. Okay. So when it comes to radiology, we are supposed to study the topic under these headings. Okay. So first thing is we need to know about the basic physics and equipment, which includes your production of X-rays, how it is being captured, and the way we have to process it. Next comes the techniques for taking those X-rays, because we have different types of radiographs, right? Be it an intraoral radiograph or a bite wing or an occlusal, and then moving on to the extraoral radiographs, your skull radiographs, your OPG, cephalogram. Then you have your 3D radiographs also. So we need to understand the techniques that have been involved in taking these X-rays. Next, after taking the X-ray, what we'll do, we have to interpret it, right? Basically, it is just for diagnosis of any kind of lesions. So we have to know what is normal to differentiate it from pathologies. So interpretation is very important. Okay. Then comes radiation protection. When radiation protection is involved, we need to understand that everything comes with a drawback or a side effect, right? Anything in science comes with some kind of a drawback or a side effect. Similarly, definitely we know that radiology has been used for diagnosis as well as for therapy also, as radiation therapy for cancers. but it also has a few side effects. So to understand that, we need to know how we can protect ourselves and also the patients from this high dose radiation. And when it comes to your interpretation of X-rays, like I already mentioned, there is something called as faulty radiographs or artifacts. Okay, so only if we know what are the artifacts of faulty radiographs, we'll be able to differentiate it from the normal X-rays. Otherwise, we'll be thinking it as a pathology only. So these are the main things that you have to study when it comes to oral radiology. Okay, see, these are the areas that you have to focus basically. Apart from that, I'll also be giving you certain key points or last minute quick learner points. Okay, so these are like straightforward questions where, for example, there can be any kind of special interpretations, right? So, or differential diagnosis aspect. So, those will be the key points that we'll be including in this topic. Okay. So, starting with the electromagnetic spectrum. Like if you see from the electromagnetic spectrum, start from the left to right. Okay, it starts with the radio waves, the low or I mean non-invasive radiation. It starts with the radio waves, then comes your microwaves, infrared, visible light, then comes your ultraviolet, X-rays, and gamma rays. So as you can see, whenever there is an increase in the wavelength, there is going to be a decrease in the energy. So wavelength is inversely proportional to your energy. So that is why your radio waves have an increased wavelength, but the energy is very, very less. On the other hand, your gamma rays have a very low wavelength. It can penetrate only to shorter distance. But the energy of gamma rays, or the penetrating capacity of gamma rays is very, very high. That is why it is used as gamma cameras for diagnostic purpose, and also it is used for as gamma knives in case of surgeries and all, right? So those have a greater penetrating power, increased energy. So this is the electromagnetic spectrum. Here you're able to see on which side is your X-rays, right? It is a kind of invasive radiation, and it is beyond the beyond the visible light in the electromagnetic spectrum. These are the two key points that we have to understand. There might be some MCQs from this portion also. I think this was asked once, which is a non-ionizing radiation. So four options have been given for you: UV rays, X-rays, gamma rays, and cosmic rays. So obviously we all know, right? UV rays is the non-ionizing radiation. Apart from it, your radio waves and microwaves are also non-ionizing radiation only. That is why your ultrasonography, which makes use of your radio waves, comes under the non-ionizing type of diagnostic purpose. Okay, so yeah, the others include your visible light, infrared, microwaves, and your radio. Okay, moving on to the X-rays. So the basic concept of X-rays is there is going to be fast-moving electrons which is going to hit on a target, giving leads to the production of your X-rays. So the fast-moving electrons are going to come from a place called cathode. It is negatively charged. It is going to hit on a oppositely charged anode. Okay, that is positively charged anode, and it is going to result in the production of X-rays. This is the basic concept. So what is the physics behind this production of X-rays? For that, we need to understand about the equipment, right? So the X-ray machine is composed of two main things: a tube head and a power supply. Okay, tube head is the component where your X-rays are going to be produced. This power supply is the one that is going to accentuate the production. It is going to facilitate the production of these X-rays. Okay, so the picture that is given here is the picture of your tube head. Okay, so the basic parts of your tube head. First comes your cathode. This is negatively charged. Okay, so remember it is on the left side of your X-ray tube. Just it's for your remembrance only. Okay, so this cathode is going to come. It is composed of a tungsten coil. Okay, so this tungsten coil only will be heated up by a power supply, which is going to release some electrons. Okay, so it is going to hit on the anode, right? So it cannot hit anywhere on the anode, but it is going to be focused by a molybdenum cup because the electron that is passing, it will be like a divergent ray, right? It has to be converged and focused to hit on a particular point at the anode. Then only the intensity will be maximum, right? So a focusing cup made of molybdenum is going to focus your electrons and it is going to hit on your anode. Okay. So the point where it hits on the anode is called as the focal spot. So the anode is the target. It's the positive target, and that is also made up of tungsten. It is embedded within a copper block. Okay. The reason why we have tungsten on both sides, that is both at the cathode and the anode, is because of four main properties. I hope you all be familiar with this, right? First thing is it has a higher atomic number. So higher atomic number means more number of electrons, basic chemistry. Second thing is high melting point. It can withstand high temperatures. That is very important, right? Because of the fast moving electrons and hitting on a target, what is going to happen? It is going to produce a lot of heat also, right? So this particular material should withstand that increased amount of temperature that has been there. So it needs a high melting point. Third is high thermal conductivity. Then only electrons will be generated, right? That is the third thing. Last is a low vapor pressure. It should not interact with any other particles. So it should have a low vapor pressure. So four main things: increased atomic number, increased melting point, increased thermal conductivity, and a low vapor pressure. These are the reasons why we are having the tungsten as the target and also in the cathode part also. Okay, the reason why tungsten is embedded within the copper block is it like I already told you, more amount of heat is going to be generated, right? So to withstand that heat, this copper block is being the tungsten anode has been embedded within this copper block to dissipate that heat that is being generated. Okay, so these are the main components within the tube head. Apart from that, we need to know something called as focal spot. So this focal spot also I think will come in your MCQs. There are two focal spots, remember, okay? One is the actual focal spot, second is the effective focal spot. The reason we have two is the actual focal spot measures 1 into 3 millimeters, okay? So where the electrons are going to converge and hit on the anode target, it is called as the focal spot, like I already told you. The actual focal spot is the entire region, okay? Effective focal spot is it is going to be even more minimized. Okay, the reason why we minimize it because we are going to reduce the scattered radiation, film fog is going to be reduced, and we are going to increase the contrast of the image. Okay, so for these reasons, what we are doing is we are trying to reduce the size of the focal spot. We are bringing that 1 into 3 millimeters into 1 into 1 millimeter. Okay, actual focal spot size 1 into 3 millimeter, effective focal spot size is 1 into 1 millimeter. So there are several advantages of reducing the size of focal spot. I think that was an MCQ once. Okay. So apart from that, you have two other variations. Okay. Initial days, there was only one stationary anode means it will be static in one position. So the electrons are going to hit at the same point. And more amount of heat is obviously going to get generated, right? There's going to be wear and tear eventually. So what they did, they tried to modify it by making a rotating anode. So this rotating anode, when you have a rotating anode, each and every time it's going to get hit on different points. So the heat will be easily dissipated, right? So stationary versus rotating anode. Rotating anode is the it's not like a recent one, but it was a later modified version. Okay, so this is your the picture shown here is your stationary anode and the second one is your rotating anode. And then obviously we need to understand one thing: there should be complete evacuation within the chamber. There is complete vacuum within the chamber. The reason, because if any other molecules are being present there, what will happen? There's going to be collision between your tungsten particle and the other particles that is being present. So we need complete vacuum within the evacuated. That is why we call it as an evacuated glass chamber. Okay. So, which of the following converts electrons into X-rays? This was quite a tricky question that was asked. Okay, it's actually easy, but quite tricky. So, which is going to convert your electrons into X-rays is the question, and four options have been given: positive anode, negative cathode. So, to understand that, we need to know one thing very clearly: if cathode is positive or negative, anode is positive or negative. So understand clearly, cathode is always negative, anode is always positive. So we're going to roll out two options from this: positive anode and negative cathode. These are the two options that you're left with. Within these two, we are asking which is going to convert the electrons into X-rays. The electrons are going to come from your cathode and it is getting converted to X-rays only at the anode, right? So the answer is going to be option A, that is your positive anode. Okay. Next is your power supply. So the reason why we need a power supply for an X-ray machine is for two main reasons. First thing is it has to heat the tungsten filament, right? So the initial current that is passing through the coil has to heat up the coil and release or produce the electrons. Electrons have to be generated from that. So the first reason is this only. We need power supply to initiate the generation of electrons. Second thing is we need to create a potential difference between your cathode and the anode. Then only these electrons can move from one end to the other, right? So these are the two main reasons why we need power supply. For that, we have two other entities that we have to know. First is your tube current, second is your tube voltage. So tube current is the tube that is passing through the cathode, that is the tungsten filament, heating the tungsten filament. It is going to pass from the cathode to the anode and it is going to return back to the cathode. Okay, it has to return back to the coil and to the main power supply. So this is the entire thing is going to be your tube current. It is measured in the units of milliamperes. Okay, for intraoral X-rays and also your OPG and your cephalometric X-rays, the ideal milliamperes is going to be between 7 to 9. Okay, mostly this is not altered, but in recent machines that come with your along with your CBCT, there are alterations for pediatric patients and also for patients who are slightly quite obese, no? So for those patients, there are slight alterations in the milliamperes and your kilovoltage potential. So the second entity is your tube voltage. So this tube voltage is nothing but your incoming electric current is there, right? You need to create a potential difference in all that. So this kilovoltage is the one that is in the form of an auto transformer that controls the um, alternating current within the entire chamber. Okay, so this tube voltage is measured in the form of kilovoltage potential. So the ideal kVp for your IOPA machines and cephalometric and OPG is between your um, 70 to 90, or sometimes it is between 80 to 120. Okay, not more than that. 70 to 90 or 80 to 120. This is the common reading that has been present. For higher X-rays like your CT, CBCT, or your 3D images, no, for that definitely your milliamperes and your kVp has to be more. Then only you'll be able to take those X-rays, right? It needs high voltage current. So for higher X-ray radiation, X-ray sources, you definitely need an altered kVp and a MA setting. Okay. So the next thing that we need to know about is your timer. So the reason why we have a timer is there is wear and tear definitely over time, right? And between successive radiation, we need to know the measure of radiation exposure that is occurring. So for that, the radiation has to be completely timed. Timed radiation only will help to prevent overexposure. So for that only, we require a timer in the X-ray machine. Okay. And next is your tube rating and duty cycle. These two imply for one important thing, that is for the successive radiation. Now we have taken one X-ray. To take you should need to know when you have to take the other X-ray, right? For that, the entire setting has to change, right? Like I already mentioned, the tube current, it has to pass from the when you click on the exposure button, what is actually happening? Your tube current is getting heated up, electrons are being produced, hitting on the target, your X-rays are getting, electrons are getting converted to X-rays, and then you're taking an X-ray image. Again, this current has to go back to the main source, right? And then the next thing has to come. So the successive radiation is possible only with these two things, tube rating and your duty cycle. Only if this is proper, the machine will not get fatigued. Okay, that is why these two are quite important to measure the successive radiation. Okay. So I think this was one MCQ that was asked. Transformer used to heat the tungsten filament of the X-ray tube. See, basically there are two types of transformers that is present in an X-ray machine. One is a step-down transformer. Second is your auto transformer. Your auto transformer is the one that denotes your kVp. That is the potential difference and all that. Your here the question they have asked, which is used to heat the tungsten filament. So we all know, right? To heat the tungsten filament, there is going to be an alternative current that is going to come from the main power supply. So the alternate current can be sometimes it will be very high, right? So we need a step down transformer to reduce the voltage of the alternating current, and it is going to make it optimal for the filament to get heated up to produce electrons. So the answer for this question is option D, that is step down transformer. Okay. Next comes your production of X-rays. So this is going to include two main types. That is that is going to bring the production of X-rays. First thing is your Bremsstrahlung radiation. Second thing is your characteristic radiation. See, in case of Bremsstrahlung radiation, you can see, right, the high energy electron is directly hitting on the nucleus, and the fast moving electron, it hits on a tungsten target. Then it is going to result in the form of a braking effect or a Bremsstrahlung radiation. That is the definition for it. Okay, so it is directly hitting on the nucleus, or there is going to be a near miss of the nucleus. Okay. So the main target here is your nucleus of your tungsten molecule only. When it comes to your characteristic radiation, what is actually happening is it is creating a vacancy site. Okay. So which means the electron that is most close to the nucleus has been attacked and it is being pushed away. Okay. So it is being pushed away and then it creates a vacancy space. So the electron from the next orbital is going to jump into this. Okay, so the potential difference between these two is going to create an energy level. This is measured as X-ray photon. Okay, this is equivalent to the measure of energy of the X-ray photon. So this is going to be your characteristic radiation. Because of these two effects only, your X-rays are being produced. Okay, these are nothing but interactions at the atomic level. Okay, interactions at the atomic level means how the electrons are going to hit on the tungsten target to produce the X-rays. That concept is there, no? It is because of these two types only. It can either be a Bremsstrahlung radiation or it can be a characteristic radiation that is going to result in the production of your X-rays. These take place at the unit level or an atomic level. Okay. Next thing is going to be the factors that control the X-ray beam. First thing is your exposure time. Like I already told you, your exposure time is for your radiation is to control your radiation exposure definitely, and it is directly proportional to the number of electrons. Okay, so if the exposure time is more, which means it is going to produce lot of electrons and more amount of x-rays are going to be produced. Because of that, what is going to happen, patient is going to have a high radiation exposure. Okay, so exposure time is directly proportional to the number of electrons, just remember that. But the energy of the x-ray beam is going to still remain constant. Okay, that is not going to be changed at all. Only the number of electrons that are being produced are going to be changed here. This is your exposure time. Second is your tube current. Again, your tube current also is going to affect the quantity of radiation, but the quality or the energy is going to be same. It is going to be a constant one. Okay. But your tube voltage, on the other hand, is going to influence the energy of your X-ray beam. Okay, which means it is going to influence the quality of radiation. Okay, so the quantity of radiation is being influenced by two main factors: your exposure time and your tube current. But the quality of radiation is influenced mainly by or only by your tube voltage. This also was an MCQ once. Okay, so an increased kVp means increased number of photons, which is going to at one particular time there is going to be maximum amount of energy that is being produced, and also we need to know the minimum threshold. So the mean energy of the X-ray beam is also being influenced by your tube voltage. So the quality of radiation is being influenced by your tube voltage. Okay. Apart from that, filtration, we need to know about filtration because there is, apart from your high energy photons, you're also going to get some low energy photons, right? So this low energy photons will contribute to film fog, or sometimes it can affect the quality of your x-rays. So to remove those low energy photons or the scattered radiation, we need something called as filtration. So there are three main types of filtration that is present in your x-ray tube. Okay, first is your inherent. Inherent means it is already present. So inherent is your evacuated glass chamber, and sometimes there is oil within the chamber. So these two are going to act as an insulation material, and it is going to produce inherent filtration to the X-rays. Okay. Apart from that, added filtration, we use a material like aluminium to be added to the X-ray tube. Okay. This is again going to reduce the X-ray exposure, and it is going to filter the scattered photons and the low energy photons. Okay. So the inherent plus your added filtration is equals to your total filtration. So this total filtration should be equivalent to 1.5 to 2 millimeters of aluminium, thickness of aluminium. Okay, it should be equivalent to that value. Okay, then only your X-ray machine is secure and it is not going to cause high dose of radiation to the patient, high radiation exposure to the patient. Excuse me. Okay, next comes your collimation. Your collimation, the function of collimation is almost same as that of filtration only. The purpose is to reduce the number of scattered photons. So collimators mostly they are of two main types, round and rectangular. The one that we commonly use in most of the X-ray machines is your round collimator, but the one that is more ideal is your rectangular collimator. The reason being, a rectangular collimator is going to resemble the same size of your IOPA, right? So what will happen beyond that? The X-rays cannot go at all, right? So there is less presence of cone cut, there's less presence of scattered radiation, and radiation exposure is also going to be very much minimal because it is going to mimic the exact shape of the IOPA film. Okay, so a rectangular collimator is the one that is ideal, but most of the machines use a round collimator only. The last one is your inverse square law. See, this one denotes only one main thing. Okay, your intensity of radiation is inversely proportional to the square of the distance. Okay, so I1 by I2 is equal to D2 square by D1 square. Just remember this. Okay, this is your inverse square law. Yeah, so the MCQ from it is, which of the following items influence the mean energy of an X-ray beam? We just now spoke about it, right? That is your kilovoltage potential. The mean energy is influenced by the kVp setting of the machine, and as it is increased, the mean energy also increases. Okay, So this influences the quality of radiation, whereas your exposure time and your tube current is going to influence the quantity of radiation, that is the number of your X-ray photons. Okay, so apart from your KBP, there's another one more thing also. The amount of built-in filtration, that is your inherent filtration, also absorbs the low energy photons. So because of that, what is happening? There is going to be increase in the mean energy. Everything is going to be high, right? All the low energy photons are going to be reduced. So the mean energy of the X-ray beam is going to be slightly higher. That is how your inherent filtration is affecting your quality of radiation. Okay, so which of the following does not apply to filtration of an X-ray beam in a modern X-ray unit? Decreases the mean energy of the X-ray beam, reducing the patient exposure by removing the low energy photons, provided by an aluminium filter required to be 1.5 millimeter thickness for 70 kVp. See, basically they're asking which one does not apply to the filtration, right? So in a modern X-ray unit, obviously we use an aluminium filter. Second thing is obviously it should be 1.5 mm of thickness. And your filtration is also to reduce the patient exposure by removing the low energy photons. The one that does not apply to it is the decrease in the mean energy. Now, just now we saw, right? Filtration is the other factor that is going to affect the quality of radiation, which means the energy of the X-ray beam. So decrease in the mean energy, that is going to be the odd one out. The answer is option A. Okay, so rectangular collimation is recommended because this one I just discussed with you. The reason is it is going to influence or restrict the area of patient's face that is exposed to the size of the receptor, that is your X-ray film or your X-ray sensor. So the patient exposure is reduced to more than half. Okay. Okay. Photoelectric interactions. This is basically the tissue level. The one that we discussed initially was at the atomic level, that is for the production of X-rays. This photoelectric interactions is nothing but the tissue level interactions. You have your Compton scattering, coherent scattering, photoelectric absorption, right? So this is something that deals with the same thing. Okay, so photoelectric interactions are highest in your enamel, dentin, cementum, and pulp. So basically, the answer is option A. Okay, that is enamel. So the probability of your photoelectric interactions is directly proportional to the cube of your atomic number. So if you consider your enamel, it has more amount of calcium, right? So and it has the highest atomic number compared to the dentin, cementum, and pulp. Since it has the highest atomic number and it is directly the photoelectric interactions are proportional to the cube of the atomic number, answer becomes option A invariably. Okay. Yeah, so this is what we were talking about, interactions at the atomic level. So any of this can be an MCQ for it. Okay, so coherent scattering, I mean, they can ask in a way like which contributes more to the formation of an image, something like that. I think there was, I mean, it was asked before, and also about these values that is given, no, like Compton scattering 57 percentage, and the other name for Compton scattering, I think that is Rayleigh scattering, right? So such kind of questions have been asked from this portion of your this topic per se. Okay, so there's going to be completely no interaction with the tissues, and the X-rays are going to hit on the X-ray, I mean the sensor or the X-ray receptor. And coherent scattering, there is going to be only 7% of interaction, and it does not contribute much. Then there is photoelectric absorption, where 27% of the incoming electrons are going to, I mean, 27% as in so much only is going to interact with your tissues. Okay, and then Compton scattering almost 57 percentage. It's like the major thing, right? And it is going to contribute for the formation of the final radiographic image. So these are the three main types of interactions. That is your Compton scattering, photoelectric absorption, and coherent scattering. So this is how your X-rays are going to interact with your tissue matter and then reach the receptor for producing the final radiographic image. Okay. So we saw, right, after passing through the tissue, it is going to hit on the receptor. So the way in which your incoming X-rays are being captured is in the form of sensors or X-ray films. These are called as receptors. Okay. So the conventional method is the conventional form is the conventional X-ray films that was initially used, and nowadays we have the digital modality, that is your digital sensors. Okay. The receptors are of two types. It can be either a conventional film or a digital sensor. This applies for both your intraoral as well as your extraoral radiographs. Okay. Because you know, right, for OPG and all, initially we used to keep a film and then take the X-ray, but nowadays it's completely digitalized because you have a sensor that is on the opposite side. You have the X-ray source on one side and the receptor on the other side. That is how your OPG machine and all works. The basic concept is all the same only. So your conventional films basically it comes in three main speeds: D speed, E speed, and F speed. Okay, so this speed of the film is going to indicate the type of crystals or the shape of crystals that is being embedded in the silver halide grains. Okay, so this shape of crystals only is going to influence the speed of the X-ray film basically, and depending on that, the amount of X-ray exposure is also going to be varied. Okay, this is one thing. And then when it comes to your digital sensors, there are two main types of sensors. One is your solid state detectors, and the second thing is photostimulable phosphor plates. Your solid state detectors is going to include three main things. Remember CCD, CMOS, FPD. Okay, CCD is charged coupled device. CMOS is complementary metal oxide semiconductors. Your FPD is nothing but your flat panel detectors. Okay, so these solid state detectors, if you see, they are direct radiography. As in, it doesn't require another medium to process the latent image and give you the final image, which means when you click the X-ray exposure button, it is there is going to be a wire that is going to be connected to a computer system. So once you click the button, the image is going to directly appear on the screen. On the other hand, your PSP is there, no photostimulable phosphor plate. That is a kind of indirect radiography, okay, which means once you click the button, what is going to happen is you'll have a sensor here, and this sensor is going to capture the X-rays and produce a latent image in that sensor. You have to pass it through a scanning system. That scanning system will produce a kind of scanning light that is going to convert your latent image into the final image that is going to be seen on the computer. Okay, so this is the difference between your solid state detectors and your PSPs. So your solid state detectors has three, right? CCD, CMOS, and PSP. Sorry, CCD, CMOS, and FPD. I'm sorry. So the CCD and CMOS are most commonly used for intraoral radiography. Okay, sometimes to your OPG also. But your FPD is there, no, that is mostly for high level imaging, like your CT, CBCT, and all. It is going to cover your apart from your dentition and your maxilla and mandible, it also covers up to your head. Okay, so it is for higher level of imaging. Okay, so this are how the X-rays have been captured, the conventional films and the X-ray sensors. Okay, so this is the image of the components in your X-ray film. Once you open the packet, you have an envelope kind of a packet, right? Inside that you have a black color paper that is to shield from exposure to the white light, because X-rays are very sensitive to bright light, so it will get exposed very easily. So to protect that only, we have this black color paper. This lead foil is to increase the scattered radiation in case of an IOPA. It is like to a very small extent only. The lead foil is going to be present only on the side of exposure. Okay, that is only on the side of the like you have your X-ray full. Behind that, you will be having that lead foil. Okay, and then the black color paper is going to completely envelop it, and over that you have this plastic wrapper. Okay. Okay, when you look at the cross section of that particular X-ray film, these are the layers that you'll be seeing. The middle layer, that is your base, is formed by a material called as polyethylene, uh, polyester polyethylene terephthalate. Okay, remember PPT. Okay, polyester polyethylene terephthalate. This forms the base of the X-ray film. It has to be super flexible, chemically inert, translucent, and there should be the reason why, because it should be completely having no interference with the image formation. Okay, so this is about the base. Then it has an adhesive on both sides. Why an adhesive? This base has to be fused with an emulsion layer. It has a double emulsion layer, right? One on top and one at the bottom. So this emulsion layer is made up of your silver halide grains. Halide means we know, right? What are the halogens? Chlorine, bromine, iodine, fluorine. So apart among that, your bromine is the more common one that is used in case of your X-rays. That is your silver bromide crystals have been embedded within the emulsion. Okay, double emulsion layer. So on both sides of the base, there's going to be an adhesive that is going to fuse the base with the emulsion layer. Okay, on top of that comes your super coat. Okay, so these are the four main layers that is being present in case of your X-ray film that you see in the cross section. So I told you about the speed of the X-ray films and the shape of the crystals, right? The first one is the flat tubular one. Second is the globular type. So as you can see, when there are flat crystals, what is going to happen? There's going to be increased surface area. So it can trap more amount of X-rays at one shot, right? So the radiation exposure is quite less. If they are globular, what is happening? It is slightly irregular in shape, right? So it needs more amount of X-rays to get trapped or to get stuck on this particular globular structure to produce an image. So the radiation exposure is comparatively higher. I don't mean that it is a very high source of radiation, but compared to the flat tubular ones, these ones have a higher radiation exposure. Okay. So your the most commonly used one, that is your speed E films, no, they are mostly globular. But your it's not a recent discovery, but higher variation, that is your speed F speed films, have a flat tubular structure. That is why the radiation exposure is very less. But one drawback is the image quality is not very good in case of your F-speed films. That is why it's not conventionally used. Your E-speed films are the most commonly used ones. Okay, you would have been using, right, a black color box. Mostly Castream only you will be using. So this Castream X-ray films are mostly your E-speed films only. Just remember that. Okay. So the speed of the film is going to correlate with the shape of the crystals. That is the shape of the silver halide crystals, which is going to indirectly link to your radiation exposure. Okay. The photosensitive component of an X-ray film is obviously the silver halide crystals. Because of that only, there is going to be trap of X-ray electrons, and it is going trap of electrons, and there's going to be conversion of electrons to X-rays. So the most important photosensitive component of your X-ray film is going to be your silver halide crystals. Okay. Yep. So moving on to the size of the X-ray films. The one that is smaller here, right? The smallest one, that is 22 into 35 millimeters. That is your pediatric film size. Then your 31 into 41 is the ideal IOPA film size. 57 into 76 is your ideal occlusal X-ray film size. Okay. Your IOPA and your bite ring uses the same kind of X-ray film only, same size of X-ray film only. Okay. And for pediatric patients, no, there was initially in the initial days they had a different one for the anteriors and different one for posteriors. But nowadays only one has been commonly used. 22 to 35 is commonly used for the pediatric patients. Yeah, this was the older one. I think this picture was taken from a very old textbook of White and Farrow. So it had different types of X-ray film for different projections. Like for adults, anteriors; for child, like it was different. And then anterior adult also it was different for bite wing radiographs. Now occlusal, I think the size was almost the same, 57 into 76. Just remember the sizes. They can ask in MCQ sometimes. Okay, so this is the picture of your self-developing film. Okay, so actually, if you see, no, it will contain the X-ray film here, and the processing solutions will be present here. So once you like exposure is also almost the same only. You have to place this part within the oral cavity, and then you have to expose it X-ray machine. So once the X-ray is being exposed, now what you'll do is you'll be squeezing this portion. So the processing solutions will go down and it will fill this area. And as you mix it thoroughly, the X-ray film will get processed and you can take it out to see the final image. Okay, so this is your self processing film. Okay. Next is a concept called as screen films. See, in case of screen films, no, IOPs don't have a screen film. This is applicable only for your extraoral radiographs. Okay. The reason why we need a screen film is for an important thing is to reduce the radiation exposure. It is something like a filter, remember, okay? So your X-ray films, we all know, right? It is very much sensitive to bright light. So this intensifying screen will have something called as a phosphor coating, and this phosphor layer, basically, it is going to trap the visible light. Okay, so it's going to be placed on top of the X-ray film within the extraoral film cassette. So what will happen is here, since it is sensitive to visible light, it is going to convert the visible light into X-rays. Okay, so once you do the exposure, X-ray exposure radiation, I mean X-ray radiation exposure, it is going to trap the X-ray electrons, and the phosphor layer in the intensifying screens will convert the visible light into X-rays. So the radiation exposure is very, very less for the particular patient. And also, if you see the scattered radiation or the low dose photons, everything is going to be removed, right? So the screen films basically are to reduce the radiation exposure only. Okay. So this phosphor layer for converting the visible light into X-rays, it makes use of certain materials called as rare earth elements. Okay. So for the emission of green light, a particular material called as gadolinium oxysulfide, which is activated by terbium, is used. For blue and UV light, for utilizing the blue and the UV light, yttrium tantalate, which is niobium activated, has been used. Okay. So there should never be a mismatch between the screen and the X-ray film. In case there is a combination mismatch, it will lead to an artifact called as mottling artifact. Okay, this was also an MCQ once. This is about your screen films. This concept will come again in digital X-rays also. I'll tell you where. Okay, so which is the disadvantage of the reflective intensifying screen base? There are four main options given for you: augmenting visible light, increasing the light emission, resulting in image unsharpness, requiring longer exposure time. See, basically, it is going to augment visible light. The first one is also correct. Second one, increasing light emission. Definitely, then only your X-ray exposure will be less. Third one, resulting in image unsharpness. That is the correct answer. See, even though it has an advantage of reducing the X-ray exposure and limiting the scattered photons and all, no, the quality of the image is not great when you use an intensifying screen. Okay, the sharpness of the image is definitely compromised here. So it results in an image unsharpness. That is the answer, and it doesn't require a longer exposure time. If there is a longer exposure time, what will happen? Radiation exposure is going to be more, right? So longer exposure time is also not happening when you use an intensifying screen. Answer here is option C. Orientation of the X-rays. This is very, very important in case of your practical aspect. So the orientation dot is there. It is always to be placed on the occlusal or the incisal aspect, and the side of exposure. The complete white color side is there, no, of the X-ray film packet that has to face the tube. If you place it on the reverse, you have the lead foil on the other side. So if you place it on that way, you're going to have a tire track appearance. That is imprint of the you have that shape in your lead foil, right? That will be present or overlapping your X-ray image. So it is going to compromise your image quality, leading to an artifact. Okay. And when it comes to your extraoral radiographs, you need to know that X-ray film has to be placed within the cassette and before the intensifying screen, so that it is completely locked, and then you have to place it on the region of interest or the side of interest. When it comes to your OPGs, in the digital OPGs, definitely the right and the left side have to be marked. Then only you'll be able to identify the side of pathology. When you're doing it manually with the help of cassette and all, no, what we used to do is we'll be placing an L-shaped mark on one corner of the cassette, so that we'll be able to identify the side of the image. Yep. So this is about the orientation. See, latent image is something like a blueprint. Imagine that way, okay? So once radiation exposure is being done, no, it is going to create a whenever you're doing a glass painting and all, what do? You actually create translucent borders and all, right? You create an imprint of the image, and then only you paint with it, right? You'll give an outline, something like that. Yeah. So this latent image is something like an outline only. It is not the final image. Only if you process this latent image, you'll be able to get the final image. Okay, so after you expose, what is happening? It is going to pass through the tissues. Whenever there is bone, it is getting stopped. Whenever there is soft tissues, the X-rays are passing through. So depending upon the intensity or density of the tissues, your X-rays are going to be stopped and passing through, and then it is going to hit on the X-ray film, and it is going to create an outline. That is your latent image. So this latent image has to be processed, right? In the manual processing and the automatic processing, the processing solutions are almost the same. Okay, we have two main solutions, actually three: developer, fixer, and water. Water is very, very important. See, like I told you, you have something like an outline, right? So we have to give a black color to that outline. So for that, what we are doing, first we have to develop that image. Okay. So for the developer solution, we have three components of the developer solution. First is your main developer. Second is your activator to activate the developer, and then you have a preservative to maintain for a particular period of time. So the developer solution is the main component is your phenidone and your hydroquinone. Okay, so this is like the dye that is going to give the border or the outline. Okay, So once you dip the X-ray film, expose the X-ray film into the developer, it will turn completely black in color because of phenidone hydroquinone. To activate this only, we use an activator, that is your sodium or the potassium hydroxide. And this solution has been preserved by a preservative, that is your sodium sulfite. Okay. So the film is going to be completely black in color now. Okay. And once you you go inside your X-ray processing room, it will be pitch dark, right? To differentiate between your developer and your fixer, obviously it will be kept in an order only, but you're new to that room, you don't know which is which means. Try to dip your hand in the solution and see. Your developer solution will be slightly alkaline in nature. It will be soapy in consistency. Your fixer solution will have a very pungent odor because of the acidic nature of the solution. Okay, that is how you'll be able to differentiate your developer and your fixer. And you all know, right? After fixing, your most of your aprons will be brown in color because of that acid only. What is happening, it is going to cause pigmentation in your clothes. So that is a very dangerous chemical. Okay, most of our first year apron, I mean the aprons have been wasted because of the solution only. So the developer solution is slightly alkaline in nature, fixer solution is acidic in nature. It is a practical point for you. Okay, so develop a solution. After you immerse the X-ray into that, it becomes completely dark or black in color because it is completely developed. The X-ray film has been developed now. Next thing, what you have to do is you have to dip it into the water. Water basically to remove the excess developer. Okay, you're going to dip it into the water and then dip it into the fixer solution. There are two main important functions of your fixer solution. First thing is to clear away the image casted by the developer. Okay, to remove the developer wherever it is not needed. Okay, so only where the areas it should be present, it should be there. The other areas have to be cleared off. That is the first thing. For that, you require a clearing agent. That is your ammonium thiosulfate. Okay, first and most important component of your fixer solution. Second thing, I told you it is an acidic solution, right? So you need a buffer, that is your acetic acid buffer. The preservative for that particular solution is ammonium sulfate. Remember, there is sodium sulfate, here it is ammonium sulfate. Okay, then your hardener. The reason why you need a hardener when it comes to a fixer is, now after you dip it in the fixer, what is happening? Your regions wherever your developer is not needed, it is getting scraped off, right? Only wherever it is needed, you have that black color image. It has to be present on the X-ray film, right? It shouldn't get washed away again. So for that, you have to fix the image onto the X-ray film. For that particular thing only, we use something called as a hardener to fix the image onto the X-ray film. Okay, so your hardener like an ammonium sulfate is very very important. After immersing it into the fixer, you're going to again wash it to remove the excess fixer. If you don't wash it, what will happen? Again, an artifact is going to be produced, a brown color blobs on the X-ray film. It will be seen. It is going to cast a brown color image. It will be like a dirty radiograph. Okay, so this is again another artifact. Okay, so developer, fixer. You need to know about the components. Any of it can be an MCQ for you. Okay, remember developer is alkaline, fixer is acidic in nature. Okay, remember developer has a developer activator preservative. There it has to have a clearing agent to remove the excess developer solution. You have a acetic acid buffer. Definitely a preservative should be present. Apart from that, hardener is a very very important one because it has to fix the image onto the X-ray film. Okay, so this is about the processing solutions. It's the same for your manual processing and your automatic processing. When it comes to your automatic processing also, these solutions are only going to be used, but the method in which it is processed only is different. Yeah. So when it comes to your darkroom equipment, I think MCQs like your the measurements will be there, no? 5 feet height and the voltage of the light, that is 6 watts. I think that was asked in your MCQ. 15 watts, sorry, 4 feet height and 15 watts. And the color is red light because your X-rays are they are not exposed. I mean, they don't get exposed to your safe. The safe lighting is your red light. Okay, they don't get. I mean, it is very sensitive to bright light, but it is radio resistant to your red filter. That is why it is the most safety thing that is used when you expose the X-rays. Apart from that, I think your penny test. Your penny test also will be asked in MCQ. Penny test, I hope you all know, right? It is to check the safe lighting in a particular room. So what they'll do is they'll place a penny, light will be switched on, and then they'll place the penny, take the X-ray, and then open it in the white light itself, and then they'll develop it and see. If the image of the penny is visible on the X-ray film, then it means the safe lighting is not good. Okay, so your penny test is to check the efficacy of your dark room. Yep. So these are the two main types of processing. One is manual processing. Second is your automatic processing. Manual, that we all mostly do, right? First you immerse it into the developer, then water, then fixer. In case of your automatic processing, it will have turbines, right? So first it will pass through the developer, then it will pass through the fixer, and last only through water. And then it has a dryer. It will come finally. It will get dried, and then it will come out. You can see here, right? Film is inserted here. Developer, fixer, water is, and then it will get dried. Manual versus automatic. Okay, so ending the era of your conventional X-ray film was by the discovery of your digital X-rays by Dr. Francis Moyen. So he was the person who discovered this, or he digitized the conventional radiographs. See, in case of conventional radiographs, the main drawback is, for example, you're taking an X-ray, I have a artifact like a cone cut, or the image quality is not good. If there's some kind of a mistake that is there, no, you cannot modify it at all, right? In case of cone cut, nothing can be done. We have to take it again only. But in case of quality, no, the contrast or brightness of the image and all, if you haven't developed it properly, in such cases you cannot do anything with the conventional one. Once it's done, it's just lost. But in case of your digital radiographs, you can adjust the brightness and contrast. You can adjust the sharpness of the image. You can zoom in and zoom out to have a clear picture. So there are several advantages when it comes to the digital radiographs, right? So the person behind that is the Sir Francis Moyen. Okay. So digital imaging or digitization. See, basically this digitization process, no, it involves a few steps. Okay. First thing is the exposure to X-rays is just the same. Instead of X-ray film, here we use the sensors. Okay. Sensors are the receptors here. So the exposure to X-rays is almost the same. And in the receptor, imagine a grid. Okay. So that grid contains rows and columns, right? So each one is a pixel. Each cube there is a pixel. Okay, so each pixel will absorb some amount of radiation corresponding to the density of the object that it is passing through. So each of this X-ray is going to generate a voltage. More amount of X-rays means more amount of voltage, and this difference between two voltages is going to create a voltage fluctuation, which results in the formation of an analog signal. So this analog signal will be captured by the computer system. It is going to program it, process it, and give you the final radiographic image. So this analog, that is the conventional to digital conversion, takes place with two main steps. First thing is sampling, second thing is quantization. Okay, so sampling means we saw, right, small amount of voltages. All the small voltage signals will be grouped together. That is sampling. You're clumping everything. Second thing is quantization. So each of these groups are going to be numbered. Okay. So each group or a sampled signal is going to be given a value. So the computer processing, what is happening? These values will be aligned within the pixel. Okay, so the pixels are organized in the matrix according to the value or the number that has been assigned to it. Last thing is, this organized pixel will display the image in the form of different shades of gray. So four main steps: sampling, quantization, processing by the computer, finally image is going to be displayed. Okay, so this is the digital analog to digital conversion. So this direct and indirect I already discussed with you. Solid state detectors and PSPs, right? I already discussed with you. So these parts I'm not going to go in detail. About, I think, CCD and CMOS, no, there was one question asked. What is the difference between CCD and CMOS? See, in case of CCD, no, these signals, they will be grouped together and then it will be analyzed. Okay, as a group, it will be analyzed. I think it's called a bucket brigade fashion, like passing a pile of buckets and then water is being passed and then going to the main pot. So here all the signals will be grouped together and it will be analyzed. In case of CMOS, you can see, right, each pixel is being connected to a capacitor here, and it will be the values will be analyzed differently. So the way in which the pixels are being read is the difference between your CCD and your CMOS. Yeah, I already mentioned, right, intensifying screens. There's something similar to that in case of your digital X-rays. That is nothing but your scintillators. Your CCD is sensitive to light, so the scintillating material will increase the X-ray absorptive efficiency by converting the visible light to X-rays. The concept is almost same as that of the intensifying screens that is being used for your conventional films. Okay. So the materials that are used as scintillators most commonly include your gadolinium oxybromide and your cesium iodide. Yeah, this point also I already told about it, right? Flat panel detectors. And there are two types of flat panel detectors, direct and indirect. So PSP is, like I already told you, it uses a scanning light to view the image. And one particular difference between your PSP and your CCD and CMOS is after exposure, no, when you have to take the next image, you need not erase the previous image. It will be automatically erased in case of your CCD and CMOS FPD and all. But in case of your older versions of your PSPs, the previous image has to be erased and then only you have to take the other image. Otherwise, double image artifact will be produced. Okay. So to erase the previous image, there were three methods that were used: exposure to intense light source, or placing it under the viewer light, or automatic plate erasing systems are the recent invention. Okay. The recent invention where the previous image will be erased automatically after passing through the scanning light, and then you can take the next image directly. Okay. So yeah, the types of scanners, no, this we saw in case of anode, right? Stationary and rotating anode. This is also a similar thing only. In case of PSP, I told you, right, it has to pass through the receptor has to pass through a scanning light and all that. So there will be only single plate system where you can place only one X-ray film at particular time, that is going to be scanned and then it will give you an image. That is the stationary plate scan. Rotating plate scan is a place where you can place multiple X-ray receptors at the same shot, so multiple images can be seen or viewed at one particular time. Okay. So stationary plate scans, rotating plate scans, two different types of scanners for your PSP. Okay. So when it comes to the characteristics of your X-rays, no, there are four main things that we need to know. First is your contrast resolution. These are the characteristics that your X-rays have to possess. Okay. Contrast resolution means what? The ability to distinguish the different densities. That is your different shades of gray are there. No, bone means it has to appear more radio opaque. Soft tissue means it has to appear radiolucent. Then in between that, different shades of gray will be there. No, between that white and the black, there are multiple levels, right? So the ability to distinguish between the different density of the objects is called as a contrast resolution. Next is spatial resolution. This is the ability to distinguish the fine details, okay, like two closely placed objects. The difference between the two closely placed objects has to be recognized by the X-rays. That is your spatial resolution. Third is your detector latitude. Detector latitude means the ability of the receptor to capture a range of X-ray exposure. Like I told you, from the most radio opaque to the most radiolucent, it has to capture everything. The ability to capture a range of X-ray exposures. This also correlates with the exposures, that is your high voltage radiation to low voltage radiation. It has to capture everything. Okay, so this is your detector latitude. Next comes your detector sensitivity. That is the ability to respond to even small amount of radiation. That is your low dose photons are there. No, it has to respond to even small amount of radiation. So these are the four main characteristics. Actually, this applies to both your conventional X-ray films as well as your digital sensors. Okay. So these are the characteristics that the receptors have to be have possessing in general: contrast resolution, spatial resolution, detector latitude, detector sensitivity. Yep. Okay. So, yeah, one MCQ that was asked: the ability of the digital detector to distinguish different densities is your contrast resolution. Yeah. So, speaking about the type of X-rays, your 2D intraoral X-rays are going to include your periapical, occlusal, and your bite-wing radiograph. So, your occlusal radiograph involves two main techniques. Okay. Speaking about the techniques, first thing is your paralleling technique, where you place the X-ray film parallel to the long axis of the tooth. Okay. So, for this, you need an external device like an XCP or mm, yeah, XAP is the most commonly used one. So basically, that is to align the X-ray film exactly parallel to the long axis of the tooth, so that the chance of cone cut has been minimized, and also the radiation exposure is invariably less. Okay, so this is about your paralleling technique. The film holders are being used here. Next comes your yeah. In case of image-based question, no, I think this was asked once. So basically, it's nothing but an endo ray. Okay, endo ray, as in we use it in case of endodontic treatment purposes, where you have to place the what that file to take to measure the working length, right? And in case of obturation, what we do, we place the master cone and then we take the master cone X-ray. So in such cases, no, when you have the normal X-ray film holders, what will happen? It is going to cause hindrance, no, while taking the X-ray. So for that purpose, what we do is we use this one called as an endo ray so that it doesn't hinder with the position of your your radiograph, I mean endodontic file or your master cone. That is your GP. It doesn't interfere with the position of that and doesn't disturb the entire apparatus while taking the X-ray. So endo ray is one thing that is most commonly used in taking X-rays for endodontic purpose. Paralleling technique for endodontic purpose. Yeah, you should understand that. Second thing is bisecting angle technique. See, bisecting angle technique, what we do is the X-ray film is placed as close to the tooth as possible, and you ask the patient to hold it, or sometimes even you hold the film. Okay, so here, if you see, no, it is completely imaginary only. There is a triangle that is formed between the central axis of the tooth and the receptor. Okay, rule that is followed here is Seysinski's rule of isometry. So two isometric triangles have been formed between the central axis of the tooth and the receptor. And when you draw an imaginary line between these two, the imaginary line that is bisecting the angle between central axis of the tooth and the receptor will produce two equal angles on either side. Okay, two isometric triangles are being produced here. That is why it is called as Seysinski's rule of isometry. So for having an optimal or having a perfect way of bisecting angle technique is we need to use certain projection angles. Only with that you will have a correct image. Okay, so the projection angles or for maxilla it is in the positive angulations, and for mandible it is in the negative. Okay, so this is the one that is ideally used for years together now. But in the recent edition of your White and Faro, I think it is the first South Asian edition or maybe the second South Asian edition, the black color textbook. In that only, I think it came around 2021 or 22. That time only that black color book was released. So according to that, no, the angulation has been revised. Okay, so where they have given for the max, the first two is for anteriors, that is your incisors and your canines. Then comes your premolars, then your molars. Okay, so for the maxillary anteriors, it is plus 45. For the canines also, it is plus 45. Premolars, it is plus 30, and molars, it is plus 30. In case of mandibular anteriors, that is for your incisors, it is minus 25. Canine, it is minus 20. Premolar minus 15. For molars, it is minus 10 to 0 degrees. Okay, so this is the revised vertical angulation. The ideal one you all will be knowing. This one was given in the latest edition. I can't say it latest because it is like 2 3 years old. I don't know if they've revised it again. Okay. So there are something like object localization in case of an impacted tooth or any kind of cystic lesion or any odontomas that is being present, no? To localize whether it is present on the buccal aspect or on the palatal slash lingual, or if it is present mesially or distally, to locate where it is being present, we use this technique called as localization technique. Okay. So there are two main techniques that have been used: Miller's right angle technique. Second thing is Flop technique or your Clark's technique. Okay. So in Miller's right angle technique, these two images depict that. Okay, right angle means two X-rays taken at right angles to each other. So first, what you're going to do, you're going to take an IOP X-ray. IOP X-ray, for example, you're taking an IOP X-ray, which is completely incidental. Okay, you see an odontome as an incidental finding between your canine and the premolar, as shown in the picture. And then what you're doing, you're taking an occlusal radiograph. So here you can locate it whether the odontome is present mesial or distally, right? So here you'll be able to locate the mesial or the distal location. And when you take an X-ray that is right angle to the IOP, that is your occlusal radiograph, you will be able to see whether the object is present on the buccal aspect or the lingual aspect. In this case, you can see an object that is present in between your canine and your premolar present on the lingual aspect. Okay, That is why a similar radiographic depiction has been shown, right? An impacted canine seen between your incisor and your first premolar. And when you take an X-ray at right angles, that is your occlusal radiograph, if you take, you will be able to see the impacted tooth on the lingual aspect. So, two X-rays taken at right angle to each other. This is your Miller's right angle technique. Second thing is your Clark's technique or Slob rule. So, this Clark technique or Slob rule makes use of two X-rays, that is two IOPs taken at different positions. So first is the it's called as orthoradial radiograph. Okay, so this orthoradial radiograph is taken at perfect angulation. Okay, see here you're going to alter only the horizontal angulation. You're not going to alter the vertical angulation at all. Please remember that when it comes to your Clark's technique, your vertical angulation, that is plus minus 40 degree, those will not be altered. You're just moving it horizontally. Okay, the first radiograph, you're taking it directly, it's exactly perpendicular to the long axis of that particular tooth. Okay, so now you're going to see an object. Here you can see it between the two premolars, right? This is the first radiograph that you're taking. In the second radiograph, what you're doing, you're moving the cone slightly distal, that is distal to the initial one. And if you see the object also moving present distally, means if it is moving towards the same side of the cone, then it means it is present on the same side, means it is lingual. If it is present on the opposite side, you're moving the cone towards the distal, but you see the object moving mesially, that is, it is seen between the premolar and the canine, means then it is known as, then it depicts that the tooth is present buccally. Okay, same side means lingual, opposite side means buccal. Okay, remember slop technique. Same side lingual, opposite side buccal. If the object is moving towards the same side of your cone, it means it is present on the lingual aspect. If you're moving the cone on one side, object is moving towards the opposite side, then it is presenting, depicting that the object is present on the buccal aspect. Okay, I hope it's clear for you. Yep. When it comes to your bite wing radiograph, no, bite wing radiograph, mostly the projection is 0 to 10 degrees only. We make use of something called as a paper tab. We wrap it around the X-ray film, the same ideal IOPA film, and we ask the patient to bite on this tab. Okay. So when it comes to an ideal bite wing radiograph, both your upper and your lower tooth have to be visible, and the apices of the tooth should not be visible at all. Okay, apices should not be visible. It should be visible only up to the maximum of the middle third of the root. Okay, but both the teeth, upper and the lower teeth, have to be clearly seen, and this interdental space is there. No, it should be exactly parallel. Okay, and basically, bite-wing radiographs are important for checking the proximal regions, the proximal caries, or the interdental intercrestal bones are there. No, intercrestal bone loss. So for those things only, we take a bite-wing radiograph, and also to evaluate the um, intercrestal bone in case of pre and post periodontal evaluation. For that, we make use of a bite wing radiograph. Okay. Next comes your occlusal radiograph. Basically, your occlusal radiographs are taken in three projections. Okay, anterior, cross-sectional, and one is lateral. Okay, this applies for both your maxilla as well as your mandible. When it comes to your maxillary anterior, no, to look at the pathologies in the anterior teeth. For that, the central ray has to pass through the tip of the nose. Remember these key points alone. Okay, central ray passing through tip of the nose is your maxillary anterior projection. That is plus 45 degree. For maxillary cross sectional, the central ray has to pass through the bridge of the nose. Okay, tip bridge. Okay, so a central ray is passing like this. So the entire cross section of the maxilla will be seen. The projection is exactly plus 65 degrees. It's plus 65. Sorry, it's a mistake. Okay, and then lateral is towards the side of interest. For example, you want to see only the right side, means you'll be moving it lateral, plus 65 degree lateral. Okay, so 2 centimeters lateral to the outer canthus of the eye, below the lateral canthus of the eye, 2 centimeter below the lateral canthus of the eye. This is the lateral radiograph. Okay, vertical angulation is almost the same, but only the side towards side of interest is going to vary. So these are the three projections for your anteriors. Maxilla. When it comes to your mandible, no, first is your mandibular anterior projection. For that, you'll ask the patient to lift their chin, and you'll be placing the central ray has to pass through the tip of the chin. You can see, right, minus 10 degree through the tip of the chin. When it comes to the mandibular cross sectional, it is exactly perpendicular to the radiograph. Okay, exactly perpendicular means 0 degrees. Okay, midline through the floor of the mouth, 3 centimeters below the chin. Okay, 3 centimeters below the chin. This is how your X-ray film will be projected. Okay, third thing is lateral, mandibular lateral. 3 centimeters lateral and 3 centimeters below the chin. This is how it will be placed towards the side of interest. Okay, so this is your mandibular lateral occlusal. So three projections: anterior, cross sectional, lateral. Applies for both your maxilla and your mandible. Okay. So 2D extraoral includes your OPG and your CEPH and also your skull radiographs and also your USG. So for your cephalometric radiograph, the size of the film is 8 into 10 inches. Your skull radiographs, it is 5 into 7 inches, and the right and left side marking is mandatory in case of extraoral radiographs. And again, like your IOPS, there is both the conventional method and the digital method that is available. So, in case of an ideal OPG, there are a few points that you have to remember. The structures are actually flattened and it will be spread out in case of your OPG. And your air spaces, pneumatic air spaces are there, no? Your mastoid air space, your ethmoid air space, frontal air sinuses, all these air spaces will be visible on the image. And your soft tissue outlines, like your soft tissue border of your nose, your tragus, all this will be also be visible here. And ghost images, these ghost images are formed by your metals, like your accessories or any kind of FPDs that the patient is wearing, dentures, your RPD dentures, and then sometimes no, the prosthetics like your crown, your implants also can cast a ghost image on the radiograph. The midline structures like your hyoid, your vertebral spine will be seen as double images on either side of the radiograph. When it comes to your skull radiographs, I have just put up like a summary. This table is given in your white and farrow. Okay, so please refer to the table and also try to remember the important projections for. There's like key projections for certain I mean certain important things like for example, if you have to view the fracture of the condylar neck, it is a reverse Towns view. And then if you have to view the paranasal air sinuses, then we'll be using the Waters view. So you have to know the key projections. Okay, just try to remember those and also try to remember the angulation of those particular X-rays alone. Okay, so I think the summary is given. Please go through your white and farrow for this table and also try to highlight the points and remember, keep it in mind. Okay, and key points, I think I'll tell you what all you have to remember. For example, you can take a screenshot of this table also. So your fracture of the zygomatic arch and the base of the skull can be best viewed using a submental vertex view. See, when you remember this table, you'll be able to answer the questions. Okay. In case in MCQ they're asking you, there's a patient with a base of skull fracture. Which type of skull radiograph will be using? So for that, what will be the answer? Submental vertex projection. So remember what are the structures and what is the best view or the best projection for that particular entity. Okay. Fracture of zygomatic arch and base of skull fracture can be best viewed by using a submental vertex X-ray. Fracture of the zygoma, maxillary sinus, and nasal septum can be best viewed using a Waters view. See, there's one thing that you have to remember when it comes to the PNS view. We have four sinuses, right? Frontal, ethmoid, your sphenoid, and your maxillary air sinus. So among these four, only three will be visible in case of your Waters view or your paranasal sinus view. One will not be seen. The one that is not seen in your Waters view is your sphenoid air sinus. To view the sphenoid air sinus, we have to take a submento vertex projection. Okay. The only sinus that is not seen in the Waters view is your sphenoid air sinus, and to view that, we have to take a submento vertex projection. Clear? Okay. So, fracture of the condylar neck is best viewed using a reverse Towns projection. Then you have medially displaced condylar fractures viewed using a PA view. Coronal process of mandible best viewed in a PA skull. Fracture of the ramus in the body of mandible can be seen in a lateral oblique 15-degree mandible. Horizontally favorable and unfavorable fractures of mandible can be seen in the lateral oblique 30-degree mandible. Okay, so these are the structures and the best views to see those structures. Yep. I think this was asked in a picture-based question once. See, basically this is a submental vertex projection only, but it is a modification. Okay, what they have done here is they have reduced the radiation to one third of the actual radiation, so that the other structures will get blurred out and the zygomatic arch will be highlighted. Okay, so this modification of your submental vertex is called as a jug handle view. Okay, so this jug handle view is to view the fracture of the zygomatic arch, where the normal radiation is reduced to one third of the radiation dose, and then you will be exposing the patient and taking a radiograph. So the fracture of the zygomatic arch will be highlighted. Okay, to view the fracture of the zygomatic arch, don't tell submental vertex projection, mention it as jug handle view. Okay, which is a modified submental vertex projection. Okay, good. So this is nothing but your TMJ views, okay? Three main TMJ views: transcranial, transpharyngeal, transorbital. Remember this way, okay? Transcranial, transpharyngeal, transorbital. So the transcranial view is taken in an open and a closed mouth projection. Basically, it is going to show the lateral aspect of the TMJ. It is like this way, right? So it is going to show the lateral aspect of the TMJ, okay? Transpharyngeal is through here, right? So it is mostly taken in an open mouth projection, and it is look at the medial aspect of the TMJ, okay? Medial aspect of the TMJ can be seen here. Transorbital is this way, right? So it is going to show the mediolateral aspect of the TMJ, okay? The entire mediolateral aspect will be seen, and it also helps in the detection of condylar neck fractures, okay? Mostly your transorbital has not been in use much because they feel the radiation has to pass through the orbit, right? So they didn't want to cause any damage to the optic nerve. So because of that, we don't use the transorbital most commonly. Okay. So when it comes to your USG, we are going to make use of radio waves, that is your sound waves. So it is going to be a non-invasive mode of radiation. And here, no, the concept is very simple. You have an object called as a transducer. So this transducer is going to act in two ways. One is it is going to reflect sound waves, and this sound waves will pass through the patient and then it will be reflected back as echoes. This will again be captured by this transducer, take it to the computer system and give you the black and white image. Concept is very, very simple. Okay. And this USG is available in the form of 2D, 3D, 4D, etc. Okay. So 2D is the usual black and white image. 3D is something like slightly orangish in color. It is like a it shows the three-dimensional variation of the object. Okay. And 4D is basically for motion capture in case of fetal movements. And when it comes to the head and neck region, the kinetics of the TMJ can be captured using a 4D ultrasound. And there is one modification of your usual USG, that is your Doppler USG, basically to look at the flow of blood in case of any hemodynamic abnormalities or any, in our language, in case of any, what's that? Um, Vascular abnormalities are there, no? So for that we can use this Doppler USG to capture that. Okay, AV malformations. Yeah, for those we can use the Doppler ultrasound. It will be something like that. And also in case of fetal observations, no, to check the fetal heartbeat. For that also they use this Doppler ultrasound. Okay, so the shape of the transducers are different, so that it depending on the area where it has to be used, the shape of the transducer will be different. We have intraoral transducers also. Okay, I think they were used in certain studies to measure the thickness of the masseter muscle, and also to check if there's any muscle hypertrophy, and also to check the bands in case of your OSMF, no, oral submucous fibrosis. For that also, this intraoral transducers have been used. I think mostly it was like in study basis only. In conventional usage, it's not much helpful, so we don't use it. Okay. So 2D to 3D conversion, there we saw it as pixels. Here it becomes voxels. Okay. Pixels mean picture elements. Voxels are nothing but volumetric elements. So 3D basically is going to include the most important ones, that is your CT, CBCT, and MRI and all that. We'll stop the class with this small concept alone. Okay. So CT basically it projects in a helical progression around the patient. So it will be spinning around the patient. Okay, it will have the sensor on one side and the X-ray source on the other side. Patient will be present in the middle. So these two will be revolving around the patient in a spherical motion to give slices of the patient. Okay, slices of the patient as image. This can be combined to give a volumetric projection also. This is your CT, basic CT. And modification of your CT was your CBCT or your cone beam CT. In case of CT, a fan-shaped X-ray beam was used. In case of CBCT, a cone-shaped X-ray beam was used. In CT, it has to move in multiple helicals around the patient. In case of CBCT, one single rotation was more than sufficient to give the entire region in a projection. Okay, so CBCT makes use of only one turn around the patient. Okay, so that is why the radiation exposure is very, very less in case of CBCT when compared to your CT. Okay, but drawback of your, I wouldn't say drawback because most of the head and neck lesions they use CBCT only. One important increased advantage of your CT is that in case of CT, the anatomic structures will be very, very clearly delineated. Nothing can come to the efficacy nothing can match to the efficacy of your CT at all. When it comes to diagnosis of your osseous structures, no, CT is definitely the best. But CBCT is more or less equally good, and also the radiation exposure is much lesser, right? So mostly for head and neck lesions, we make use of CBCT instead of CT, unless and until it is very, very essential. Okay, so these things are not very, very necessary for you. This difference I've already spoken to you. Yeah. Scan volume basically depicts the region of interest only. Like if, for example, you need only sectional CBCT means the FOV is going to be reduced, and that is the field of view will be reduced. In case you want the entire maxilla and the mantle means the FOV has to be adjusted accordingly, and it can even cover up to the skull. Okay, so the FOV can be increased even up to covering the skull of the patient. Okay, so the FOV can be adjusted according to the region of interest. Applications, obviously, we all know this. Yep. When it comes to an MRI, no, again it makes use of another non-invasive source, that is your magnetic source. And basically, what happens is the patient is being placed inside a high intensity magnetic field. Okay, like 3 Tesla. Nowadays, I think 4 Tesla is mostly present. Tesla is the measure of the magnetic field. Okay, it's not car. It's measure of the magnetic field. So 4 Tesla, I think, is the recent one. So you're going to place the patient within a strong magnetic field, and there's going to be movement of the hydrogen atoms in the human body when it interacts with the magnetic field. Okay, so because of those variations, what will happen? These variations will be captured as in the form of energy by the magnetic field, that is magnetic field capture that is set up within the MRI machine, and this is going to convert the energy into the black and white radiographic image. Okay, so the alteration to the hydrogen atoms caused because of the frequency of the magnetic field is going to be captured as an energy by the computer system. It is going to convert it into a black and white image to give you the final radiograph. Okay, this is your how your basic principle of your MRI. So, difference between your CT and MRI, most commonly we all know, right? For looking at the pathologies of the osseous structures, we prefer, that is the bony structures, we prefer a CT. And for soft tissue structures, MRI is more reliable. But CT, no, it actually has a soft tissue window also. But the most reliable, obviously, is your MRI only. But CT also has a modification. We need to know that, okay? And in case of CT, no, one most important thing is Hounsfield units. This was named after the person who invented, and I think this can be an MCQ for you. Most commonly, they'll be asking you the CT unit for water, air, and for bone. Okay, so most commonly we make mistakes in this only. Always remember, most dense object is going to have the highest CT unit. Okay, so bone is the most dense object in your body, right? Apart from your tooth, your bone. So bone, the CT unit or your Hounsfield unit is plus 400,000. This is like the maximum one. And water is neutral, right? Water is colorless, tasteless. It is completely neutral. So remember, water has a Hounsfield unit of 0. And air, on the other hand, okay, air is like it's totally unpredictable. No, think it like a negative. Okay, so it is minus 1,000 for air. Bone, it is plus 1,000. Air, it is minus 1,000. Okay, In between, water is neutral, so it is zero. Okay, remember this. Yeah, if you want, you can take a picture, or I think it's given in your textbook also. CT Hounsfield units. It can be an MCQ for you. Most commonly, they have asked about these three only. Okay. CT versus MRI, if you see, no, the variation comes in the way we take the X-ray. In case of CT, like I told, no, there is bony window and soft tissue window and all that. In case of MRI, we don't call it as projections or anything. We call it as a sequence. Okay, T1 sequence, T2 sequence, flare sequence, and there's positron weighted imaging, PWI. So all these are like sequences only. So mostly your T1 sequence is to look at the anatomical structures, and T2 sequence will help view the pathologies. Okay, just remember so much. Yeah, this is about your CT, like I already told you, and nuclear imaging. So, nuclear imaging, what we do is we inject the radioactive isonucleotides through the patient's body, and this will go and fill the areas of pathology, and the image will be captured using a gamma camera, which is going to highlight the area where the isonucleotides have been uptaken. For example, no cancer cells are there. So, these cancer cells have the ability to uptake the isonucleotides, so it will get highlighted, okay, in the when we view using a gamma camera. So this is the basic principle of your nuclear imaging, and under that only we have your PET, SPECT, and all that. Okay, so PET comes as the expansion of your PET is your positron emission tomography, and SPECT is single positron emission tomography. So these are the radioactive isotopes most commonly used. I think in this you'll be familiar with your endocrine tumors. For that we use iodine, and for bone it is technetium 99M. These are the most commonly used ones. And combined imaging. So this is nothing but like a fusion imaging. Okay, even though this nuclear imaging is a very useful tool, it has a drawback. Okay, so the pathological structures, the anatomical structures are there. No, it is not very clearly delineated. The anatomical framework is there, no, it's not clearly seen. For that purpose, what they did, they tried to fuse it with CT. I already mentioned, right, CT is like the perfect for delineating the anatomical structures. So what they did was they combined the SPET with CT and SPECT with CT. It's also called as fusion imaging. Okay, yeah. I think we'll see this in the next class. From cyanography, I'll be discussing about radiotherapy, and also we'll be seeing a little bit about interpretation and faulty radiographs. Okay, thank you so much. We'll wind off with this today. Thank you.